Section 7.3 is on complex numbers in polar form. This is another section where we're really just introduced to this idea, but we don't go into too much detail. But most likely this is a topic that you may see in later math or engineering classes. Okay, first let's just review complex numbers. So a complex number is written in this form, something like a plus bi. And the a we would call the real part of the number, and the b, which has the I attached to it, we would call the imaginary part. And so technically when we're talking about an imaginary number, we're talking about something that has an I attached to it. But when we talk about a complex number, it could have just a real part, just an imaginary part, or it could be a combination where there's both a real and imaginary part. The notation that we're going to use in this section is that for these complex numbers, we can use the letter z. So some examples of complex numbers. Here's this first one, z1, 6 plus 2i. What I want to look at now is how to graph a number like that. So to graph it, we would graph it on something called the complex plane. So the complex plane I have here, notice that what we consider as normally the x-axis is now considered the real axis. And what we normally think of as the y-axis is the imaginary axis. So if we think about our part A and part B, the real is referring to the value A, and the imaginary is referring to the value that we have for B. So if we wanted to plot 6 plus 2i, that means 6 on the real axis and 2 on the imaginary axis. So it'd be equivalent to plotting the point 6, 2. So I'm going to go 6 on the real axis, 2 up, and that's the point. I'm going to label it as z1. Now let's look at z2. Negative 3 plus 5i. So I'm going to go negative 3 on the real axis and 5 on the imaginary axis. So that's going to be right here, which is, if it were the xy plane, would be equivalent to plotting the point negative 3, 5. I'm going to label that as z2. And then let's get the last two plotted as well. 1, negative 4. Here we have z3. And then finally z4. So negative 8. And I'll rewrite this one, because if you just have a negative I, that's the same thing as saying negative 8 minus 1i. So the b value for that case is negative 1. And so that point would be right here, and I'm going to label that as z4. So this is how you plot complex numbers. Okay, let's look at the polar form of a complex number. So we've talked about complex numbers as the form a plus bi, but we can actually also write complex numbers in polar form. So this is the equation for that, and I feel like at first glance it looks pretty complicated, but it's honestly an extension of all of the ideas we've already seen in the trig class so far. If you notice, we've got the r value in the front, but if you multiplied through, that would be r cosine theta plus ri, oops, let me rewrite this, I times r sine of theta. So even from what we talked about with polar coordinates in general, we talked about how cosine is our x value and sine is our y value. And that's kind of following from, even though we're on this complex plane here where we have a real axis and an imaginary axis, it's like those things are all still hand in hand. So we use the y value to represent the imaginary part. That's indicated by sine in this case. And the x is still indicated by cosine, and that's our real part. The last thing I want to mention from this page is what's called a modulus. And a modulus is basically what we've been looking at with hypotenuse. So it's the same thing there. It's the length of that line on the diagonal. And we can find it by typically using the Pythagorean theorem. So for this first z value, we've got 3 plus 3i, so it's kind of in this form a plus bi. One thing we want to find is the modulus. So that's written in absolute value form here. So it's the same thing as using the Pythagorean theorem. I'm just going to write it all at once. So that's the square root of 3 squared plus 3 squared. And so we get the square root of 18. So modulus is equivalent to the r value as well. So we're going to say that r is equal to the square root of 18. We could simplify the radical a little bit if we wanted to. So we could rewrite r as 3 square root of 2. Now we want to convert this to polar form of a complex number. So first I'm going to write what that is again. So that's z is equal to r, and then we have cosine theta, which is representing our x, plus I sine of theta, which is representing our y. So we have our r value. Right here I'm going to plug in 3 square root of 2. But in order to finish, we need to figure out what is theta. And so the way that we can figure out theta, I'm going to go ahead and draw what we normally would for our angles. The point 3i would be 1, 2, 3, 1, 2, 3, right here. And so even though we're working in the complex plane, we can actually do the same process that we had been doing in terms of drawing angles in standard position. So here I have a triangle that's represented by this angle theta, and we're going to try to find theta now. So we know that the sides, the legs of the triangle, are 3 for the x and 3 for the y. So we can go ahead and use the Pythagorean theorem to find the hypotenuse. But before I actually do this, I don't know if, we haven't dealt with our special triangles. We haven't dealt with 3 and 3, but we have dealt with a triangle that has the same length for both the x and the y. And so based on similar triangles, I can actually do that instead. So that's a 1, 1. And then we know that as being one of our special triangles, so that would be square root of 2. So why is this the same? Well, think about this. If you figured out tangent of theta here, that would be opposite over adjacent, which is 1. With our similar triangle is basically that you could take the legs and the hypotenuse and multiply or divide by the same number, and all the angle values will be the same. So that's what a similar triangle is. So in this case, that would be tangent of theta, tangent of theta is equal to 1 over 1, which is 1. So that's telling me the angle measurement is going to be the same, because for either triangle, tangent is going to be 1. So what's the angle for this? Well, when I write it in kind of this form, like our special triangle, the angle here is 45 degrees. Which is the same thing as pi over 4 radians. So how we want to write our answer kind of depends on what it says in the problem. So here we says we want theta to be between 0 and 2 pi. So because that's listed in radians, that's telling me that the answer should also be in radians. So then I'm going to go ahead and write the final answer here. So that's z, our complex number, is in polar form 3 square root of 2 times cosine of pi over 4 plus I sine of pi over 4. Now let's look at the next example. First, let's find the modulus. So the modulus is the same thing as our r value, so we have an r value of 20. Now let's try to figure out the value for theta. So if we have 10 square root of 3 minus 10, and at least when I draw this, I don't need to like plot it exactly. I'm really just trying to figure out what quadrant it falls in. And so in this case, the x, or the real is moving in the positive direction over here, and then I go down 10. So that means that my point should be somewhere down here in quadrant 4. And so I'm going to go ahead and try to start drawing the angle like this. And so this time I'm actually going to not use the value theta. I'm going to write this angle as alpha instead. And the reason that I'm doing this is that because it's in quadrant 4, what I first want to find is the reference angle. So I'm using alpha to represent what the reference angle is, and then I'm going to convert that to the actual angle, which I'm going to call theta. The actual angle here would be rotating from 0 in the counterclockwise direction. But first thing I need to find is that reference angle. So if we put the values down here on the adjacent side, that's the 10 square root of 3, and then the opposite side is negative 10. So it's possible that when you see this written down, it may be triggering a special angle that you do know, and that we've used a lot in this class, which is that over here, I didn't really write it in that first example, but you could look at it as if you divide each side by the same number, that ends up being square root of 3 and negative 1. So this is part of the 30, 60, 90 triangle. And so in that case, the hypotenuse is 2. And so the alpha value, the reference angle is 30 degrees, and in radians, that would be pi over 6. So we're almost there. I just need to convert this to that actual angle, theta. So based on the location here, I want to find theta when my reference angle is pi over 6. So to figure that out, I could go and say that theta is equal to 2 pi, which would be if we rotated around one full rotation, but subtract that reference angle. And so whenever working with radians, it's good to get common denominators. So I can multiply the 2 pi by a 6 over 6. So that would be 12 pi over 6 minus pi over 6. So that angle that we're looking for is 11 pi over 6. So let me write down again the form of the complex number in polar form. So that's r times cosine theta plus I sine theta. So to get our final answer, we just need to plug in these values. So we found r, we plugged that in here, and we found theta, and we're going to plug that in there. And then that's going to be our final answer. So we've got z is equal to 20 times cosine of 11 pi over 6 plus I sine of 11 pi over 6. Now let's take some complex numbers in polar form and then convert them to rectangular form. This process is actually a little bit more straightforward because it's really just evaluating these trig functions and then plugging in the values. So in this case, we need to figure out, well, what is cosine of 5 pi over 3? You might be in the habit now of drawing your triangles. Hopefully you are. In this case, 5 pi over 3 is actually in quadrant 4. And it has a reference angle of pi over 3. And that's just because if we did 2 pi minus 5 pi over 3. I'll write it this way. We end up with 6 pi over 3 minus 5 pi over 3, which is a way that we could get to that reference angle of pi over 3. That's one of the special triangles, so let's fill in our values. So pi over 3 is the same as 60 degrees. So across from the 60 degrees goes the square root of 3, 1 on the other side, and then the hypotenuse is 2. Once I fill in the values, then I check the signs. So in this case, 1 should be positive, and then square root of 3 should be negative. So let's start plugging this in. Cosine of 5 pi over 3 is going to be 1 over 2. Sine of 5 pi over 3 is going to be negative square root of 3 over 2. So we've got 18 times 1/2 plus I times square root of 3, negative square root of 3 over 2. And then from here, we can just keep simplifying. One thing I would do after plugging in sine and cosine is just to distribute that r value. So that ends up being 9 plus I times negative square root of 3 over 2 times 18. So I haven't quite simplified that yet. I'm going to rewrite this as 9 minus 9 square root of 3i. One thing that you might have noticed that is different is that when we write it in polar form, we kind of put the I in front of that imaginary part, where when we write it in rectangular form, we write the I afterwards. But then this part in yellow is our final answer. Okay, let's do this again for the next one. We need to figure out cosine and sine of 180 degrees. So when it comes to one of the 90-degree angles, instead of using triangles, I think about it as a unit circle. So 180 degrees is over here on the x-axis, on the negative side of the x-axis. So a point on the unit circle would be the point -1, 0. Here's the x, here's the y. Cosine corresponds with the x value, and sine corresponds with the y value. So I'm going to go ahead and plug all of that in. So we've got 7 times cosine of 180 degrees is -1, plus I times sine of 180 degrees is 0. So the I part goes to 0, so there's no imaginary part. And the final answer is -7. And we could still call this a complex number. It just happens to be a complex number that has a real part and no imaginary part. The last thing that we're going to look at in this section is something called de Moivres theorem. So this theorem, which is given here, is not something that you need to memorize, because for our exams you're going to be given this formula. So this formula is used to find exponents, and it's to find exponents when you have a complex number written in polar form. So let's try to apply this formula to this first example, example 4. So we've got, what's happening is that we've got in here, this is our complex number, 4 times cosine of 4 pi over 15 plus I sine of 4 pi over 15. And something you might have noticed about these complex numbers now is that the theta values are always the same, and that's exactly what we have going on here. But we're trying to also take this complex number and then apply this exponent of 5. So the n value from the formula in this case would be 5. So let's go ahead and try and rewrite it using de Moivres theorem. So z to the 5th power is equal to r to the n. So in this case, that's 4 raised to the 5th cosine, and then now it's not written as an exponent, but when we apply it to the angle, you actually multiply it by that number. So it's going to be cosine of 5 times 4 pi over 15 plus I sine of 5 times 4 pi over 15. So we can simplify each angle. So in this case, we can cancel out a 5. So both angles will end up being 4 pi over 3. And then we can also figure out 4 to the 5th. Let me rewrite that. So 4 to the 5th, if you plug it in, it's actually 1024. Now times cosine of 4 pi over 3 plus I sine of 4 pi over 3. If we wanted the answer to be in polar complex form, then this would be our final answer. But if we check back to the instructions here, we were actually trying to find the final answer in rectangular form. So the last step here would be to convert this to rectangular form, which again, to do that, is we need to figure out, well, what is cosine of 4 pi over 3 and what's sine of 4 pi over 3? Let me draw the angle. So 4 pi over 3 is just pi over 3 past pi, since pi is the same thing as 3 pi over 3. So we've got an angle here, and now we're dealing with quadrant 3. Pi over 3 is the same as 60 degrees, so across from the 60 degrees is square root of 3, 1, hypotenuse 2. Now I want to check whether it's plus or minus for each one. So the thing about quadrant 3 is both x is negative and y is negative. So both those values should be negative. So if we try to evaluate cosine and sine now, cosine of 4 pi over 3 is going to be the adjacent over hypotenuse, so that's negative 1/2. And sine of 4 pi over 3 is going to be negative square root of 3 over 2. So let me rewrite this, but plugging that in. And now I'm just going to go ahead and switch the order of the I to put the I at the end here. Distribute now 1024 to each one. And that leaves us with negative 512 minus 512 square root of 3 times I. That's our final answer in rectangular form. In this last example for this section, we're going to use de Moivres theorem. The difference here is that our original number that we're given is actually in rectangular form. So in order to use de Moivres theorem, it needs to be in polar form. So we're going to take this number, convert it to polar form, use de Moivres theorem, and then since we do want our answer in rectangular form again, the last step will be to convert back to rectangular form. So that may actually seem like a lot of steps to solve a problem like this, but if you think about it, if we did leave it in rectangular form, this would not be an easy problem to solve, because raising it to the 6th power, I guess I'll just write it all down, would not be easy to do. So one might argue that it would actually be easier for a problem like this to convert it to polar form and use de Moivres theorem. So first let's convert it. So in order to convert it, we need the modulus first, the absolute value. So in this case, that's the square root of square root of 3 squared, and then remember, when you have it written like this, square root of 3 minus I is the same thing as saying minus 1I, so that b value is negative 1. So plus 1 squared so the r value is 2. Now we need to figure out theta. So if I have a number like square root of 3 minus 1, square root of 3 goes in the positive direction. I shouldn't put tallies there because it's not 3. And then negative 1 moves in the negative y direction. So it should be an angle that ends in quadrant 4. Square root of 3 minus 1i. Now I want to work to find the angle, and I'm going to label this as alpha instead, just to indicate that I'm first going to find the reference angle, and then I'm going to find the actual angle, theta, where this rotation is the actual angle, theta. So if I put the values here, the x is square root of 3, so that's going to go on this adjacent side, or the x side, negative 1. So this is one of our special triangles that we've already looked at. Hypotenuse is going to be 2. So that tells us that our reference angle in this case is 30 degrees, which is the same thing as pi over 6. So our actual angle is going to be 2 pi minus pi over 6. So we've got 11, let me write it all out. 12 pi over 6 minus pi over 6, which is 11 pi over 6. One thing, though, that I'm thinking about is so 11 pi over 6 is correct. But as we know with angles, there's more than one answer, because you could add or subtract a full rotation and it would be the same answer. The reason I'm tempted to write this a different way is just because I know I'm going to have to apply the de Moivres theorem. Part of de Moivres theorem is where you have to multiply n, which is in this case is 6, by the angle. So that's going to make this angle a little bit bigger. But to try and simplify it, since it's not like those other problems where I was trying to get my answer between 0 and 2 pi, I don't have that restriction right now, so I could write anything. So I'm actually going to write it instead as negative pi over 6. So negative pi over 6 falls in the exact same spot as 11 pi over 6. You could do that by saying that when you are in quadrant 4, the negative indicates a rotation in the clockwise direction, so that becomes negative pi over 6. Or you could say that it was 11 pi over 6 minus a full rotation, if we think about coterminal angles, which still gets us to negative pi over 6. So this is what I'm going to use for our theta value. So all this work I've done so far will just get me to not actually evaluate the exponent of 6 yet, but just to rewrite it in polar form. So to rewrite it, it's going to be r, which in this case is 2, times cosine of our angle, which I'm writing it as negative pi over 6, plus I times sine of negative pi over 6. So this is rewriting the complex number square root of 3 minus I, but then I want to apply that exponent of 6. So I want to raise this whole thing to an exponent of 6, and that's when I use de Moivres theorem. So that's going to be 2 raised to the exponent of 6 times cosine, and now I'm going to do 6 times negative pi over 6 plus I sine of 6 times negative pi over 6. Simplify that. So 2 to the 6th, we get 64. Cosine, our angles, or 6 over 6 are canceling. So it's cosine of negative pi plus I sine of negative pi. This would be the answer in polar form, but because we were trying to convert back to rectangular form in the end, we have a little bit more to go before we're done with this problem. So cosine of negative pi, we've already talked about that. That's the same thing as the cosine of 180 degrees. Because if we go in a negative rotation, 180 degrees or pi, it still ends up right over here on the x-axis. So the answer is going to be 64 times cosine of negative pi is negative 1 plus I. Sine of negative pi is 0. So this gets 64, or not 65, 64 times negative 1 plus 0. So the final answer is actually negative 64. Ooh, that's a lot of work to get to the answer of negative 64, but that's what we end up in this case. All right, and so there is more that's covered in our textbook, but that's the part of section 7.3 that we're going to cover in this class.